Welcome back to the Deep Dive, where we tear open source material, extract the most important insights, and make sense of the knowledge you need fast.
Today, we're taking a journey deep into a world it's built on mathematical elegance and abstraction.
We're talking about functional programming, and specifically, Haskell.
It's arguably one of the most intellectually rewarding corners of coding,
Huh?
and we're zeroing in on a single short line of code that I think perfectly encapsulates the elegance and the power of the language.
Yeah, this is a snippet you might see when working with command line parsing. It looks like this. Parser, empty helper.
And if you're not a Haskell programmer, that looks like, total gibberish.
Absolutely. But if you are, you know that line is doing a huge amount of work. Our mission today isn't to decode the whole thing. That gets into some advanced concepts like applicatives.
Right, we're not going there just yet.
No, we're peeling back the first two foundational layers, the stuff you have to get before anything else makes sense. We are diving into partial application and this amazing shorthand called operator sections.
And this is so much more than just a syntax lesson. The source material for this deep dive was brilliant because it gave us this big picture hook right away. It said the key to understanding that line, and really functional programming in general, is seeing the difference between a regular function and a wrapped function.
And we're focused squarely on the regular function mechanics today.
Exactly. Because if you can't see how cleanly Haskell handles a normal calculation, you won't appreciate the genius of those more complex wrapped structures later on.
Okay, so let's unpack this and start with partial application. It's a concept that's absolutely central to how functional languages operate,
Yeah.
but it often sounds super technical and intimidating.
It really shouldn't. The term itself just means applying some, but not all, of a function's arguments.
Okay.
And think of it like a highly specific custom order machine. It knows what it needs to do the final job, but you only hand it the first few parts.
And then you just set it aside.
You set the partially fed machine aside, yeah. It's ready for the final input later. The key is it doesn't return an error. It returns a new function.
That's a perfect analogy, because in most imperative languages, if you have a function that needs two inputs and you only give it one, the compiler it yells at you.
Right. Missing argument.
Yeah, exactly. But Haskell is built differently. And this ties directly into how functions are even represented, right?
Yes, and the source material reminds us of a crucial notation distinction here. Most standard functions in Haskell use what's called prefix notation.
Meaning the function name comes first, then its arguments.
Right.
Like fxy.
Exactly, like sin x in math.
Oh.
But then you have operators, plus signs, multiplication signs.
And those use infix notation. They sit between the arguments, like 1 plus 2.
So let's use a simple two-argument function to really illustrate partial application. Let's imagine a function called, say, add two numbers. Takes x and y and just returns their sum.
Okay.
If we look at its type signature in GHCI, the Haskell interpreter, we'd see something like num a, LA.
And let's translate that string of symbols for anyone unfamiliar. That num a apart just means this works on numbers.
Right, it's a constraint.
Then the arrows tell the story. It takes an argument, the first a, and then what does it do? It returns a new function.
That's the key. It returns a function that takes this second a, and then that function finally returns the result, the final a.
So it's not really a two-argument function.
Not really. This is a fundamental concept called currying. Every two-argument function is secretly just a sequence of one-argument functions. So if we only apply the first argument, if we type add two numbers 10, we haven't finished the calculation.
You've created a brand new single-argument function.
Exactly. And the type signature shrinks. If you check the type of add two numbers 10, it's now just num a. It dropped that first a because we've already supplied it.
So it's now a specialized tool? It's a function that is just permanently set to add 10 to whatever you give it next.
And that concept right there, that applying one argument to a multi-argument function just creates a simpler function, that's the entire engine behind partial application, and it's the gateway to the next, much more interesting idea.
Operator section.
Operator sections.
Right. So if partial application is the basic engine, operator sections are like the high-performance fuel that lets Haskell code be so concise. It's what people call syntactic sugar.
That's a great way to put it. An operator section is essentially a syntactic shortcut. It's built to leverage partial application, but specifically for those infix operators.
The ones that sit in the middle, like plus and do.
Right. An operator section transforms that infix operator into a prefix function simply by intentionally holding back one of its arguments.
It's forcing something designed for the middle into a role at the front. And you do that just by wrapping it in parentheses and giving it only one of the two things it needs.
Precisely. The classic example you see everywhere is the expression +1.
Right.
When you see that operator and value inside parentheses, your brain should immediately translate that to, this is a function that takes one input and adds one to it.
Hang on. Why does Haskell need the parentheses for operators? We didn't need them for add two numbers.
That is a fantastic question. It gets right to the heart of the grammar. If you just wrote +1, Haskell would just read that as a positive integer, the number 1.
Ah, okay.
The parentheses are the signal to the compiler. They say, hey, treat this operator and this value as a single unit, a function, and assume the missing argument is coming later. It's an explicit instruction to partially apply that operator.
And when we check the type signature of +1 in GHCI, we get that beautiful simplified result again.
Num-AA.
It's confirming it.
Yep.
We've made a function that expects one number and spits out another number.
And that's the power. Suddenly, we have this tiny anonymous function, a mini tool that we can pass around. We can use it immediately, like +1, 5 gives you 6.
Sure.
But more importantly, we can use it inside other, more powerful functions. This ability to turn basic arithmetic into reusable first-class functions is why Haskell code just looks so clean, so mathematical.
Okay, so now that we get the basic idea, boxing up the operator, and one argument, we hit a critical distinction. Because operators need two things, right? One on the left, one on the right.
Which means there are two fundamentally different functions you can create.
And this is section 3, the difference between a left section and a right section.
Yeah, and this isn't just some, technical detail. It completely changes the mathematical behavior of the function you create.
Okay, so let's start with the one we just talked about, the right section.
A right section is when you provide the value on the right side of the operator. So our example, +1. When we treat this as a function, the missing variable is implicitly on the left side. It's waiting for x.
So its equivalent is like fx equals x plus 1.
Exactly. It will always add 1 to whatever you give it.
Which means, conversely, the left section is when you provide the value on the left side of the operator. So that would look like 1 play.
And that creates a completely different function. In this case, the missing variable is on the right side. It's waiting for a y. So its functional equivalent is fy equal 1 plus y.
Okay, now hold on. With addition, 1 plus and plus 1 give you the same result, because addition is commutative, the order doesn't matter.
Right.
But this is where we really need to stress test this. What happens when we use an operator that is not commutative, like subtraction or division?
This is the perfect test. Let's take subtraction. Say we want a function that subtracts 10 from every number we give it.
Okay, so that means that 10 is on the right, it's a right section, 10.
Perfect. So if we apply that to, say, 50, 10, 50, the missing x is the 50, the occupation is 50 minus 10.
Which is 40?
40. But what if we accidentally use the left section?
10.
Then the 10 is fixed as the first argument. We're waiting for the number to subtract from 10.
Exactly. So 10, 50 becomes 10 minus 50.
Which is negative 40.
A difference of 80. I mean, that shows these two syntaxes, 10 and 10, they generate two completely distinct functional behaviors. You have to be precise. Let's do division. It makes it even clearer. Say you have a data set, and you need to calculate the inverse of every number. You need a function that does 1 divided by the number.
To do that, we have to fix the numerator as 1. We're waiting for the denominator, so the 1 has to go on the left. It's a left section. 1. So if we give it 4, 4.
We get 0.25.
Correct. But if you accidentally wrote the right section, 4, the function becomes, take whatever input you give me and divide it by 4.
Which, with an input of 4, would give you 1.
Yeah.
Totally different result. It's so important to slow down and realize that the parentheses and the position are not just decoration, they are defining the exact mathematical transformation.
It's the highest level of detail you can get without defining explicit variables or lambda functions. Which brings us
to the final piece of the puzzle.
To the final piece, yeah.
Here's where it gets really interesting for me. What is Haskell actually doing to make these sections work? We keep calling it syntactic sugar, but what's being sweetened?
We're going to prove that an operator section is nothing more than a beautifully compact shorthand for a lambda abstraction.
Which is programmer speak for an anonymous function.
An anonymous function. The language designers just realized that people were constantly writing these tiny single-use functions just to wrap around an operator, so they built the syntax to save keystrokes.
So instead of writing the function out the long way, we get this streamlined notation. Let's take our function from earlier, +1.
Okay. The verbose longhand way of writing that exact same function is with a lambda. X mass x plus 1.
Right, the backslash signals the lambda, the x is the input, and the arrow points to what to do with that input.
Mm-hmm.
And you're saying these two things, +1 and x is +1, are identical.
Functionally identical, and we can prove it. Our source notes have the technical proof. When you check the type of the operator section in GHCI +1.
We get that familiar result, numa equals a.
And now when you check the type of the equivalent lambda abstraction would x mass x plus 1.
You get the exact same type signature.
The exact same one, numa a, applet a. The compiler sees them as the same functional entity. The section is just the clean, pretty way of writing it.
This is the true aha moment. Because now you can see the immediate practical impact on writing clean code.
Mm-hmm.
If you want to use a higher order function like map to apply something across a whole list, look at the difference.
Let's say you have a list of prices and you want to apply a 10% tax.
Okay.
Using the lambda, you'd write something like map, price 1.1, list of prices, which it's readable, sure, but it's a little clunky.
There's some boilerplate there. You're defining price just to use it once.
Exactly. But if you realize multiplication is an infix operator and you can partially apply it.
You can create the function 1.1.
And the code becomes map 1.1, list of prices. The clarity is just phenomenal. You're describing what the operation is, not the mechanics of how to do it.
Wow. Okay, so to recap, we started with this esoteric line of code, and we've decoded the basic mechanics that let functional languages like Haskell be so dense, yet so powerful.
We covered partial application, the idea of functions waiting for arguments.
Then operator sections is the shortcut for that, and the crucial distinction between left and right sections.
And most importantly, we established that an operator section is just a nice way to write a lambda abstraction, giving us this elegant tool for composing functions. It shows how Haskell is designed to turn simple arithmetic into reusable, first-class citizens of the language.
And this level of abstraction lets you focus on the flow of logic, not the mechanical steps. However, as we said at the very beginning, our source material insisted on a critical distinction. The difference between a regular function, which we just mastered, and a wrapped function.
We've just seen how simple and elegant it is to create and manipulate a regular function using these operator sections.
Which raises an important question for you, the listener, to mull over. If a regular function is created so easily with this simple syntactic sugar, what additional complexity must be involved in creating and manipulating a wrapped function in a functional context? And why is that complexity even necessary for something like that op-parse applicative parser to work?
That complexity is really the cornerstone of understanding how Haskell handles side effects and these powerful patterns like applicatives and monads, and it absolutely sets the stage for our next investigation.
Until then, keep digging into those source materials. We'll see you next time.